talking to you all. I'm Professor John Remedios. I'm Director of the National Centre for Earth Observation here in the UK, which is, has staff in 11 universities and 3 research organisations.
And I'm Frank Martin Seifert. I'm working for the European Space Agency in its Earth Observation Centre in Frascati in Italy. And welcome to everybody here.
So during the show, we'll be asking you a couple of questions which you'll find on Slido. So if they want to show the Slido QR code for a second, it'll be up there for a minute, and you can take that code and answer the question, I hope. If not, we'll be showing it again in a little bit, and it should be available as you're in the queue, hopefully. So what we're trying to do today for you is to give you some sort of insight into the dynamic forests, which are the largest collections of trees and the most dense, and therefore the most important for carbon dioxide. We know this is of real concern to everybody, so what we're trying to do is illustrate for you what is it about those trees that's important, what is about those forests that's important, and what we're doing for the future. You'll notice the title said something about lungs for the world, lungs of the world. So in a way, that's a bit of a misnomer, because actually, if you think of lungs as producing oxygen, most of the oxygen in our atmosphere now comes from oceans and ocean biology. But if you think of it about breathing and think about the trees responding to sunlight returning to their hemisphere, then it's in the sense of carbon dioxide being used in photosynthetic activity of the trees. So just get that sense of forests actually absorbing that carbon dioxide as a process that happens very importantly in our globe all the time. Just a few things about forests before we get to our main speakers. There are about 3 trillion trees or so, with some uncertainty about that. And there's roughly 8 billion humans. So something like you each have responsibility for about 375 trees, if you want to look at it like that, okay? So just remember that, 375 or 400 trees, they're yours. Some facts from the World Resources Institute that we've picked up, who are one of our partners in this. For reference, here perhaps a hectare is about 10 meters, 100 meters, sorry, by 100 meters. Scotland's about 8 million hectares. So forests in the world are about 4 gigahectares, so about 500 Scotlands. Since the turn of the century, we've probably lost about 400 million hectares of loss. And roughly speaking, every year, we're losing something like 20 million hectares. And more than 50% of that is in the tropics, and a large part also particularly in what we call the humid tropical forests, which are really important for carbon storage and biodiversity. So we need to be really concerned about the consequences of that, and I'll return to the facts around that at the end. So what I want to just say for the moment is we welcome the Deforestation Pledge. We're committed to monitoring it, and we're committing to putting missions into space which do that. So let me hand over to my colleague, Frank Martin.
Well, coming from a space agency, I'm of course passionate to watch the forests from out space with satellite data. But I'm as well as you, a human being who likes to walk around in forest, to enjoy the smell of a forest after fresh rain, to look for mushrooms. So forest is not only about carbon, forest is as well about biodiversity. It's a livelihood for people. It is a place where you have a great diversity of fauna and flora. And it is a place which is providing a lot of ecosystem services towards us, the 8 billion people on the planet. And in this minute when I'm speaking, we are losing, just to give you a more figurative number, 27 football fields of forest.
Thank you, Frank Martin. So now we're going to talk a little bit as part of this introductory session to have some inputs from some people who couldn't be here in person. Perhaps that's good because they're not flying here. Can I start with Sylvia Wilson, who is from the United States Geological Survey, is the manager of their Silver Carbon program.
Hello, I am Sylvia Wilson and I am with the United States Geological Survey. I'm a forester and a remote sensing specialist. For the past 10 years, I have been working for the Silver Carbon program. a U.S. government program that builds technical capacity on forest monitoring to report to REDD+ and other related forums. Silva Carbon as a program doesn't do this alone. We are part of a bigger initiative, the Global Forest Observation Initiative, known as the GFOI. GFOI is an informal partnership that brings together countries and donors to accelerate progress on monitoring and accounting carbon emissions from land use change. GFOI-led partners are Australia, Norway, the United Kingdom, the United States, the Committee of Earth Observation Satellites, CEOS, the European Space Agency, FAO, the World Bank, among others. And these partners coordinate their activities under 4 interlinked GFOI components. The 4 components of GFOI that we show in this slide are coordinated by the GFOI Secretariat based at FAO. These 4 components are led by different partners and have different roles. The capacity building component delivers complementary and consistent capacity building and is managed by the Silva Carbon Program and FAO. The methods and guidance components develop user-friendly guidance for REDD+ and is managed by Australia. CEOs coordinate the data component and supports the availability and accessibility of remote sensing data and other data sets as well. And the research and development component is led by Wageningen University and develop R&D activities responding to country needs. There's 2 successful outcomes of this collaboration among components. One is the REDD Compass, and the other one is the Open MRV platform. The REDD Compass is based on the Methods and Guidance book, and is an online tool that walks you through all the necessary steps to develop a monitoring system, from the institutional arrangements in the country needs to the reporting scenarios. And the Open MRV is a repository of operational tools with examples and user manuals available to technical teams in countries. A success story of the GFOI partnership is the development of an alert system in Peru. With the assistance of Silva Carbon, University of Maryland, WRI, and other members of GFOI, the Ministry of Environment and the Government of Peru implemented an early warning system for deforestation. These alerts are showcasing their GeoBosques platforms, and they have been used to inform policymakers and law enforcement, and also used by their citizens. We have many examples where a partnership of a GFOI partnership can achieve more than any program alone. Thank you very much for your attention.
So thank you, Sylvia. So our next video is from Laurent Durieux, who is the SDG coordinator, that's the Sustainable Development Goals coordinator, of an organisation called GEO, which is the Group on Earth Observations. And he's in the secretariat there. And this is an organisation which brings together governments across the world to use satellites in space for benefit of mankind. So Laurent's video, please.
Hello, I am Laurent Durieux, SDG Coordinator at the Group on Earth Observation Secretariat, known as GEO, and I will explain a pilot project on tropical forest assessment in Mozambique using big Earth observation data and artificial intelligence processing. The contribution of the forest to the mitigation of CO2 emissions currently discussed at COP26 is essential. To reverse the persistent rates of deforestation and forest degradation, there is an immediate technical opportunity. This is coming from the fast-growing availability of Earth observation data from satellites and the new data handling capacities using cloud-based storage and artificial intelligence. Together, these new technologies offer what was identified by the World Bank as a second generation of deforestation and forest degradation monitoring, reporting and verification that we call MRV 2.0. This will boost the reporting capacities for REDD+ under the United Nations Framework Convention on Climate Change, as well as other carbon finance frameworks. GEO has a leading role in the deployment of MRV 2.0 and is contributing through specific activities dedicated to forest observation from space, such as the Global Forest Observation Initiative, GFOI, and GeoTrees. Complementary to these long-term initiatives, the Coalition for Rainforest Nations, which leads the international REDD+ negotiations, funded a pilot project to test the applicability of MRV 2.0. This was done with the most systematic and consistent Earth observation data from Landsat satellites and using advanced artificial intelligence techniques. Under the coordination of the Geosecretariat, the coalition proposed that big Earth data experts from Brazil's National Institute for Space Research, INPE, collaborate with the government of Mozambique. This includes National Forest Inventory experts from the National Directorate of Forestry, the National Directorate of Climate Change under the Ministry of Land and Environment, and the National Fund for Sustainable Development under the Ministry of Agriculture and Rural Development. The goal is to develop consistent annual land use and land use change maps, as well as forest cover assessments for the entire Mozambique territory at 30-meter resolutions comprising the period from 1990 to 2020. The program is using specific open data cube technology provided by INPE to organize more than 50,000 Landsat images that cover Mozambique over a 30 years period, in addition to more than 80,000 in-situ samples provided by the Mozambique partners to train the artificial intelligence algorithms used to classify Landsat image temporal series. Amazon Web Services provided free cloud credits from the Amazon Sustainability Data Initiative to process this data. The 30 annual and interannual land cover and land cover change maps will help institutions in Mozambique to estimate their national greenhouse gas emissions and to deliver REDD+ information. During this project, the experts from Mozambique will be trained to create and process the Earth observation data cubes so that they may continue such advanced monitoring on their own. All data cubes will be made available on the Digital Earth Africa platform for the entire continent to facilitate broader use of this data. INPE also intends to transfer the data processing capacities to the CIPAL platform of the Forestry Department of the United Nations Food and Agriculture Organization. If you would like more information about this project, please contact the Geosecretariat. Thank you.
So that was, I hope that kept you interested, and we're going to move on now to some live presentation. So can I welcome Professor Matt Disney to the stage. So Matt Disney is at UCL, University College London, and is a member of the National Centre for Earth Observation.
Thanks, John. So if we could have the film as well, please.
My oak might just have started growing when Wellington won the Battle of Waterloo in 1815. But finding out its age is just the beginning. I want to know what other secrets my oak holds at this time of year. Tony has invited Dr. Matt Disney to my garden to reveal some of my oak's summer secrets. He scans trees all over the world to explore exactly how they help the planet.
So we've stripped away all the other trees from our three-dimensional picture, and we're left with your splendid oak here. So one of the things that we can do is we can estimate how many leaves there are on your tree. Would you like to have a guess?
I couldn't begin to guess.
So we reckon there are about 260,000 leaves on your tree. So that's about 3 tennis courts worth of leaf area.
I'm told that all those leaves are helping the tree to breathe in more carbon dioxide, which it will then use to grow more branches.
So the other thing we can do, we can measure how long the branches are in your tree. So over the course of our work over the last few years, we've been all across the tropics, and we've scanned somewhere between 10 and 15,000 trees in total. And so far, we found trees that are a lot taller. One of the biggest trees we found was in Ghana, and that tree had nearly 9 kilometres of branches. And when we saw that, we thought, wow, that's amazing, 9 kilometres of branches. Your tree's bigger than that.
Of course it is.
Your tree has 12 kilometres of branches in it.
A prize tree?
Indeed. So far, that's our longest
Really?
branched tree.
Is it? I'm very, very proud of it. All those branches. My oak must be a very healthy tree. And in 200 years, my tree must have breathed in a lot of carbon dioxide.
So I didn't want to tell her that we've actually found trees with a lot more branches than that subsequently. So you see us, we set this equipment up during that making of that documentary, and Phil, my colleague here, was helping me set that up. And one of the things I wanted just to show very briefly was how we're using these kind of new measurements to improve our understanding of how much carbon is stored in trees and forests. So we all know what a tree looks like. This is my daughter's primary school when asked to draw trees. They're all kind of recognisably trees, but you know, there's all sorts of variety, and that's one of the key things about trees, is there are so many shapes and sizes. So if we want to know how much carbon is stored in forests, we have to weigh those forests. And if we want to weigh those forests, we've got to weigh individual trees. And that's very, very difficult to do, because you have to cut them down, you have to dry them, and you have to weigh them. And of course, not only is it very hard work, but you don't want to do it if you can avoid doing it. So how do we do it? It was very kind of Dame Judi Dench to help us demonstrate how we do that. And essentially, we can measure trees using this kind of equipment in very high detail and estimate the mass of these trees. So what we've been doing over the past few years is building up an understanding of, when you look at the size and shape of a tree, how much mass and how much carbon is stored in it. What does that have to do with satellite data? Well, the crucial thing is, when we want to estimate how much carbon is stored in forests from satellites, we have to go from what we can measure, the kind of height and density of the forests, to how much carbon is stored in individual trees and then spread out over these 3 trillion trees that John mentioned. So we have these relationships between height that we can measure and then the biomass, the carbon, that we can't measure. And so what we do is, typically, we're taking samples of a very small number of trees where we know what they weigh, and then we're extrapolating that to the 3 trillion trees on the globe. And there are good relationships between height and biomass, but understanding how those vary is really important. To do that, you need to measure the trees in fine detail. So this is what the number of trees in a tropical forest plot in Malaysia looks like. Some of these trees are 70 metres tall. And what we're finding is that although, you know, the trees have a kind of size and shape that we're all familiar with, the variety of the size and shape isn't captured so well in these simple relationships. So making this kind of measurement is helping us build better models to understand and derive carbon from satellites. So I'm going to finish on that note, and what I want you to do is to ask yourselves, how much carbon do you think was stored in Dame Judi Dench's tree? How much do you think it weighed? So I think we have the Slido of that. If not, just think about the size and shape of that tree. It's 200 years old and it's about 25 metres tall. So does it weigh 100 tonnes, 15 tonnes or 25 tonnes?
You can scan the QR code and hopefully put your answer in, and we'll be monitoring the answers, and we can see some answers going up as we speak. Great, excellent, keep them coming. I'm not sure if it's possible to join in online, but please do if you can. Okay, so I'm going to hand over to my colleague Frank Martin and the next panel, Observing the Trees and the Carbon. So if Paul and Sean want to come up.
So the next speaker is Paul Palmers. He is from University of Edinburgh, professor for Earth observation. Please, Paul, the floor is yours.
Next slide, please. Oh, yeah, okay. Okay, so what I'm going to be talking about today is atmospheric CO2. And the atmosphere is a general dumping ground for CO2, we'll see in a moment. This first slide is what we call the carbon cycle, and there's various components to it. So you see at the surface, fossil fuel combustion. We all know fossil fuel bad. It's emitting something like 34 petagrams. Petagrams is scientific jargon for billions of tons of CO2. It's a massive amount. The amount that stays in the atmosphere, we know that really well because we have lots of measurements, really accurate measurements. And you can see that, roughly speaking, just over half remain in the atmosphere. And what's happening is that the land, the forests, vegetation are taken up at about 60%, and the oceans taken up about 40%. We've also got a contribution from deforestation. So when you cut down a tree, can't take up carbon dioxide anymore, is also you're also burning, so that's also emitting CO2 into the atmosphere. So what I'm going to be talking about is CO2 and how it relates to the other components. So this figure on the left, this is a tree with some grass, and we know from our school photosynthesis and respiration. So during the growing season, photosynthesis is the dominant process. So this is when the trees take light and convert it to chemical energy, drawing in CO2 and water and producing oxygen and carbohydrates. And carbohydrates are the building blocks for biomass. So things like stem, stump, branches, all that stuff that Matt's just talked about in the tree, that's biomass, above ground biomass. And of course there's below ground biomass as well, lots of biomass in roots. And that's all sensitive to human intervention. When we look at the atmosphere, what that looks like is on the right-hand side. So you'll see this should be a fairly familiar plot. So you'll have a steady increase in atmospheric CO2. That's primarily due to combustion. But you'll also see, if you looked at sort of a monthly scale, you'll see this seasonal cycle, this sort of undulation in the atmospheric CO2. And that is the Earth's land and ocean emitting CO2 and then drawing down CO2. So that reduction is during the growing season, absorbing CO2. So how do satellites measure atmospheric CO2? So these are a very simple diagram. So see, these satellites that we use are orbiting the Earth around about 700 kilometers above the Earth. They are sensitive to a very small percentage of the atmospheric CO2 that they see in the column, less than a percent or so. So they require extreme precision. What they use is sunlight. So sunlight comes, it's lots of wavelengths, passes through the atmosphere, reflects and comes back up again. Now, during the journey of that light, it passes through an atmosphere which includes CO2. And atmospheric CO2 is absorbing light at certain wavelengths. Excuse me. And the satellite can sensitive to those particular wavelengths, and it can change. They can determine where the CO2 has been absorbed, and then convert that to how much CO2 is in the atmosphere. So that's essentially what happens. This is a movie of what the satellite is seeing, if you saw all at the same time. And the date is in the bottom left. You can see that we're now in April already. So when we just move to the northern hemisphere summer, so it's June already, you're starting to see the blue colours becoming more prominent. And that's when the CO2 is being taken up by the forest vegetation. And as we move to the summer in the southern hemisphere, you'll see that you should see that the forests in the southern hemisphere are taking up CO2. But you also see the reds in the northern hemisphere there. These are places where North America, China, Europe, they're emitting CO2. So there's quite a large, you're looking at quite large gradients in CO2. This is the last slide. So where we take all that very rich picture of atmospheric CO2, we can change that. These small changes in atmospheric CO2 can be related to the emissions and uptake. And I won't bore you with the details, but these are some of the results that we have. So the one on the right, so this is the Amazon basin, the Congo basin. These are examples of how these forests have responded to the El Nino. Which, if you're familiar with the El Nino, it's a very large-scale climate variation. The Amazon basin actually was a net release of carbon dioxide during El Nino, and it's slowly recovering, different parts of the Amazon recovering at different rates. The Congo basin was also a large source of carbon dioxide, and now it's beginning to recover, and we're starting to see the uptake where you can see the negative annual flux there. China is another result that we found quite recently. And what we found was that large-scale afforestation pursued by the Chinese government has led to a net sink of carbon dioxide for southwest China. So there are things that we are beginning to see around the world by virtue of these satellite observations where we haven't had observations there before. I'm going to move on to my colleague, Sean.
Next speaker is Sean Quigan, professor at the University of Sheffield, and he will introduce you to measurement of biomass from space. Okay. He is as well the science lead for the CCI biomass and for our biomass mission to be launched in 2023.
Hello there, everybody. Tuesday's Declaration on Forests and Land Use was a recognition that the forests have a major role to play in climate, and that's through forest biomass, which is where you store carbon when a forest grows, which is the carbon that gets lost when a forest is destroyed. So forests have a major role to play both in the carbon problem and in the carbon solution. So what do we actually know about biomass? The answer is not enough. And the reason for that, in fact, there are two reasons. The first is that the forests on the planet are huge, and they're difficult to access, and they're remote. For example, the Amazon is 2 million square kilometers. So we only have a very limited coverage by ground measurement of forests. The second reason is that it's not easy to make measurements on the ground in forests, either by cutting them down, which you clearly don't want to do very often, or indirectly by measuring, for example, the diameter of the trunks and converting that to biomass. And even measuring the trunks can be something of a problem when you're dealing with the monster on the right, for example. Okay, so over the last 20 years, a major scientific goal of the space community is to find ways of measuring or weighing forests from space. And that relies on two key technologies, which I'm going to illustrate by the next little video. Okay, the central idea here is that you have a sensor which transmits radiation, which can actually penetrate through the leaves and hit the trunks and the branches below where most of the biomass sits. And then what gets reflected back, you gather at the sensor, and you infer the biomass from the signal which comes back. Two types of sensors can do this. One is radars, and the other one is lasers, and we usually call them LiDARs, actually, because it's to do with the measured distance as well. So worldwide maps of biomass have been made using these two technologies. This is just sections from different worldwide maps. The one on the left is from radar, the one on the right is from LiDAR, and the one in the middle is from LiDAR as well, but it's just being built up. It's a sensor which is in space now, is aiming to produce, currently be the most accurate of the biomass measurements from space. However, a problem we have is that none of the sensors which are in space at the moment, except for the middle one, were designed to measure biomass. They were designed to measure ice or soil moisture or land subsidence. And so when the maps we've got now are all represent a struggle with dealing with not ideal sensors. The space agencies have responded to this weakness splendidly. And currently there are 3 missions which are specifically designed to measure biomass from space. The first off the blocks is by NASA, so it's a real Bill Whizzy presentation, so I'll let it speak for itself. Okay, and that's in space now. Laura's going to tell you more about it in a moment. The next two are radar sensors, and this is the mission I lead. It's the biomass mission, which will launch in 2023. Use a long wavelength, 70 centimeters, which is the best possible for sensitivity to high biomass forests in the crucial tropical zone. Okay, but at the same time, launching around the same time, is the NASA Indian Space Agency NISAR mission, which uses a wavelength of about 24 centimeters. It's a bit shorter, so it's not as sensitive to high biomass, and this will be ideal for lower biomass forests. And what you can see is that you've got 3 missions in space around about the same time, and this is going to be a golden age for measuring biomass from space. And so one of our key drives is to learn how to combine all 3 missions together to make the very best measurements of biomass from space. The other thing that's part of this is it's not just space missions, but the collaboration between the agencies and between the satellite people and the people measuring on the ground has been absolutely outstanding. There's been nothing as good as this for that sort of level of cooperation in the past. And I'm now going to get Laura to speak to you. She's speaking from University of Maryland. She'll tell you more about JEDI and how we intend to put these missions together. Thank you.
So I think there's a video to play, pre-recorded, but I think someone has to press play on it.
So that's Laura Duncan then from University of Maryland, and she will tell us about the JEDI mission.
It's on.
Thanks very much.
Is it on the slide? Just come on.
Thanks very much, Sean.
No, I'm doing my best.
So I'm here to represent the...
No, it's not playing.
It was sound. You could hear a voice. Just play it again.
Thanks very much, Sean. Hi, so I'm here to represent the NASA LiDAR community or space laser community and talk about some of the new missions we have at NASA and how we're using them to map forest biomass. All right, so the first of these is NASA's JEDI, which Sean already talked about. And JEDI's been on orbit for almost 3 years, collecting literally billions of LiDAR, what we call waveforms, LiDAR observations, which are measurements of how tall the forests are on the planet. We have 3 lasers up on the International Space Station, and each of them illuminates about a 25-meter diameter on the circle. So we have these laser shots, and in each of those shots, we collect one LiDAR waveform. And so what this technology looks like is that you have a sheet of photons coming down from the laser, and the top photons reflect off the top of the canopy and come back to the ISS first, and then the last photons are reflected off the ground. So the distance between those gives us the height of the canopy, how tall the trees are, and the area under this curve we use to estimate forest biomass. And so NASA has launched JEDI back in December of 2018. So it has been on orbit for a while, and you can see the animation on the left. This is how the JEDI data collection works. So the longer it's in space, the more and more detail we get about the Earth in 3D. So we turn the JEDI data into these estimates of forest biomass, and the biomass products from JEDI, some of the footprint level ones, shot by shot, have been online for just over a month now, but the gridded products are coming out very, very soon at a 1 kilometer spatial resolution. So we're very excited about JEDI. We're at a very exciting place in the mission. And here you see a JEDI animation on the left. But there is a very substantial data gap because the International Space Station does not go over the poles. So the astronauts never have a bird's eye view down to the North Pole or to Antarctica. And so we're missing most of the very important boreal forests, those northern forests that cover huge swaths of land and are changing quite rapidly because the North is heating up more than anywhere else on the planet. So in order to map those important northern ecosystems, we fortunately have a second NASA LiDAR instrument in space right now aboard NASA's ISAT-2. So we're borrowing from our colleagues in the ice community and using their LiDAR, which is really designed for mapping ice topography and ice sheet melting and glaciers melting. But we're using it for mapping forest height and biomass. So we just released our sort of draft product for our boreal-wide biomass map with ISAT-2 and Landsat, which is at a 30-meter spatial resolution. And together between ISAT-2's boreal biomass product and the JEDI biomass product, we have global NASA LiDAR coverage and biomass products from LiDAR missions. So these cover 2019, 2020, 2021, and hopefully onwards. So the JEDI products, the ISAT-2 products, these are not the only products out there. We have a lot of different types of technology like radar, which Sean talked about. And so different groups are making biomass maps using different flavors of satellite data and different statistical approaches. So we, the scientific remote sensing community, has tried to get together and make sense of these products. And so to do that, we're actually launching a brand new platform for COP26 for this meeting. And we're doing this as what we're calling a biomass harmonization activity. So we're taking all of the brand new maps, putting them on one shared platform and trying to understand the relative strengths and weaknesses of different approaches. We're also partnering with a handful of pilot countries to do validation of these new products in those countries and explore them for policy application. And Joanna will talk about that in a little bit. So I just wanted to show you what this dashboard looks like. You can go to this website today, zoom into some area of interest to you. Here's an example for looking at the products in the Congo Basin. And so if you are interested in how much biomass there is in your area of interest, you can start to explore these products. So here's a NASA JPL map, here's an ESA CCI biomass map, and here's an NCEO Africa map. So you can see that there are discrepancies between these products, and we're trying to resolve that scientifically, but they generally do all capture the same gradient of biomass. If you want to get involved with this process, you can also start looking at these products in an area that's familiar to you. So let's zoom out and zoom over to the UK and look at the products there. So if you want to help us, you can interrogate these products in an area where you're familiar with. Maybe you've been hiking in some place close to where you live, and you can start looking at these products and see if they make sense to you. You can always flick on and off the layers and look at the underlying imagery. And if you think that the products are not performing perfectly or are performing very well, you can always give us feedback. So here on the ISAT2 product form, you can give a little bit of feedback as to how useful those products are. Nope. Okay. I think that this actually was an outdated video, so I think we can pass it along from there to the next speaker. But thank you so much. And the last thing that I'll say in the slide that was cut out is that no matter what amazing technology we put into space, we really need that ground component. We can't tell how good our products are without what we're calling the fourth mission, which is the ground component, which Matt Disney will talk about a bit more. So thanks very much. We'll pass it on from there.
I think we should thank Laura. So thank you, Laura, from joining us all the way from the United States early in the morning. So can we move on to our next group of people? So Joanna, if you'd like to come up and speak. Yeah, thank you.
No, it's fine. You can stay. Hi there. You can stay. Hi there.
Chairs.
I'm a forester, and I'm a forester by training and also by passion. And I've been working with in tropical forests doing these measurements that you've been seeing, but in collaboration with national forest inventory teams and greenhouse gas inventory teams. And the objective of these teams is to use this information, analyze it, and prepare the reports to submit to the Climate Change Convention. Oh, I should have.
Can we have the slides again, please? Just forward it if you
forward
it past the... Oh.
Next one.
Yeah.
Bear with me.
Here we are.
Okay. So this is very exciting what we've seen. And from the country perspective, what we want to know is how can we use this data in our reporting and to fulfill the obligations we have to the convention. And what's exciting with this is that the scientists and remote sensing experts, they are very keen to contribute to the processes, and they are taking this data, promising data, and producing new maps that are global, that are consistent, that are transparent. They use transparent data and transparent methods. So that's very powerful, and for us in the countries, it's very interesting to have this additional data that we can use in case we don't have any, or even if we do have our plot data, our system, our national forest inventory in place, we can always benefit from adding this additional information to compare with our estimates. And why is that? It's because of the transparency of the Paris Agreement and for the fact that all of you here in this audience can use these products and keep countries accountable. So you can all use it and see you're not keeping with your promises. So from the country perspective, we want to know that. We want to know if there are differences between our estimates and the products and the maps. And we want to understand why there are differences. And what I love about this initiative from CEOs and the space agencies is that they're getting together as scientists and addressing some of the pressing and the outstanding questions, but they're also engaging and collaborating with countries because we need to have the greenhouse gas inventory experts also are part of these discussions. And why? Because these experts, the national experts, they know the methodologies. They know what are the equations. They're familiar to the equations and the variables. So for each one of these equations, we need data for biomass. So if the remote sensing experts and the scientists want to produce data, they need to collaborate with the greenhouse gas inventory teams to understand how what are the characteristics of the maps, what characteristics the maps need to have to be suitable to be used in these equations, and how can we handle the data so that they are suitable for these equations. And I'll give you an example of something that can happen if we do things separately. So here in this equation, we need to know this is something that can happen in our country, and we need to report that to the convention because that's our obligation. So here we had the conversion from forest land to cropland. And what do we need? We need the information on the biomass before the conversion, the B before, and the information on the biomass after the conversion, the B after in the cropland. And the scientist will look at this and say, yes, I can help you. We have satellites. I can tell you what is the mean biomass of that large extent of forests that you need to know. So, okay, as a user, I'll say, okay, I'll use it. That's nice. But then I'll look better into it and I'll see, well, actually, in fact, you are considering forests that you are considering trees that are not forests in my national definition. Those are tree crops. These are cashew trees. That's not forest. Or these are trees outside forest. These are mangrove trees. So I don't like this. I don't like this. Thank you. I won't use it. So instead of reaching to this situation, let's work together beforehand and understand what are the limitations and how can we handle the data and use it for our objectives. And this is just one example with a national definition. There are other things to consider. The fact that we also here we report anthropogenic emissions and not from natural causes, and also other issues of scale, temporal resolution, temporal coverage, consistency, and the IPCC principles also accuracy. And the accuracy brings us back to this CEO's initiative that Laura talked about, and that's bringing together the two groups of scientists, space agencies, and national experts to test the maps. First of all, we have several different maps. We'll use national data to test it and to know if they're good or not. And the second exercise is to go a little further and try to understand or to have the practical implementation of the 2019 guidelines. So in these guidelines now, there's a mention to the potential use of biomass or of satellite data to produce biomass estimates, but he doesn't say how to do that. He highlights some of the issues that need to be dealt, but he doesn't say how to use it. So we need to explore that together, and this is an example that we've been working in collaboration with Paraguay, with a team from the US Forest Service and Infona, the Instituto Florestal Nacional de Paraguay. And I think, yes, here in this case, Paraguay has a very good forest plots system, but they're also trying to use JEDI to complement this. So they are going to prepare their new measurements, and they want to see if the JEDI can give them any information to plan the next round of measurements. Are they going to measure the same plots, new areas? What do they need to do? And JEDI gave some good information on that. And I'll pass the word now to, I think, Christina from Infona.
Hello,
everyone.
No, she'll be online, hopefully.
I think we heard a hello.
No, the hello is the video, I think.
Oh, video. Okay. Well,
I think we have with us online either Cristina from Infona or Regino Acosta.
Regino.
Oh, I'm sorry that Cristina couldn't connect, but should I?
Yes, hello everyone. Hello, Joanna.
Hi, Regino.
So, Regina, welcome from Paraguay.
Yes, I am in Paraguay now.
Excellent, thank you. Here we are, there we are.
Okay, first of all, I'm going to send you the apologies of Cristina Goralewski. She has technical issues. For this reason, she can reconnected with us now. Well, let me talk a brief introduction about this work. This work is going to be start for the CEO's initiative. It's for sorry, second, I have a problem with my screen. Don't worry. Okay, this work born from the CEO's initiative to show the important contribution of the satellite, the Earth observation satellite data for the achievement of the objective of the Paris Agreement and the global inventory process. Our country was selected for this initiative since Paraguay has presented its forest emission reference level within RED Plus delineation in 2016. It also has a national forest inventory and a technical team with experience in the use of remote sensing tools. In this context, a collaboration team has been formed that explored and approached the update and supplement the estimated national biomass through the integration of satellite image and data from the plots of the National Forest Inventory. Property mainly its observation of the JEDI instrument from NASA. From the participating team members of the biomass modulation group of CEOs, the United States Forest Service, and the National Forestry Institute, with the important support, like always, of Silva Carbon, and my promote of the initiative. Today we are presenting the result of this work, considered a great scientific contribution to the country. Science is the potential to be applied for various purposes in the pursuit of improving the quality of national data. And well, next we will share a video with the scope and challenge that this work has proposed to us here in Paraguay. Thank you so much.
Thank you, Regina. So if you play the video.
I am part of the NCI team at the National Forestry Institute in Fona. We have carried out this work with the important collaboration of the team of Ferg Bullock, Sean Helly, Joanna Mello, and Shikian Yang, with the support of Silva Carbon and the contribution of the Paraguayan team with Ermelinda Villalba, Victor Benitez, and Patricia Spram. A brief review of the fieldwork procedures applied at the national level consists in, first, the sample units are selected for each stratum. Second, the design of plot is carried out, which are unique for forests with fragmented continuity, and cluster for forests with a continuous structure. And finally, the deployment in the field to carry out the measurement and collect the data for its corresponding calculation. For this work, we are piloting a methodology in Paraguay that integrates remote sensing and forest inventory data into a model to estimate above ground forest biomass. The model uses LiDAR measurement from the JEDI mission, a Landsat tree canopy covered dataset, and forest tape information to predict biomass at our field plots. These datasets are especially explicit and therefore cover the entirety of Paraguay's vast and often inaccessible forests. After calibrating the model, it can be applied to create two primary outputs: a map of biomass and statistical estimate of mean biomass and this margin of error. Our preliminary national estimate of biomass is 66 megagrams per hectare, which is consistent with the 69 megagrams per hectare reported by the FAO in 2020. There are numerous advantages to this methodology. First, it's a quick and affordable way to update our previous estimate of biomass. Second, it can be applied to varying spatial domains to obtain an estimate of biomass for a specific region or forest. And finally, it makes it possible to measure biomass in forests that are not accessible by land. This approach can complement our existing forest inventory and show promise for other countries that have yet to establish a national forest inventory.
Okay, so thank you. To complete this part of the series, we're going to invite Professor Matt Disney back again, who's going to tell us about biomass reference measurement sites and networks and reveal the answers, I hope, to our Slido questions. So if you haven't yet answered, get there and put your answer in. Oops.
So there's the answer. So you're about the best audience I think I've ever had when I've asked this question, because you clearly went for the right answer. It's 25 tons. So that tree essentially weighed 25 tonnes dry, and of that, about half of it is carbon. So there's about 12.5 tonnes of carbon stored in that tree over the 200 years of growth of that single oak tree. That's pretty amazing. And like I say, it's often spread. Nobody goes for 15, but quite often it's about 50-50 between 25 and 100. But so well done. If we go back to the presentation then, I just wanted to mention very quickly that the emphasis has been put on the importance of ground-based measurements. And there are many kind of initiatives in measuring forests at a kind of hectare scale on the ground going on for ecological reasons, for conservation reasons and so on. But there's never really been a consistent way of doing this from the biomass perspective. And that's partly because we haven't had this rich array of new instruments in space. So a key part of one of the things that we're trying to develop now is to say, okay, we've got these new instruments either in space now or coming online. We want to build on all of that work that's being done on the ground in a way that's consistent, so that we can do it consistently for carbon stocks and biomass from one place to the next. So we can compare our satellite observations to ground-based estimates, not just in one place, but everywhere. And to do that, we need to establish or build on existing work to pull this stuff together and do it in a way that's really, really consistent. That means investing in working with collaborators on the ground in all these different parts of the world, and in particular focusing on the tropics, because so much of the carbon is stored in tropical forests. So the GeoTrees initiative is aimed at doing that, establishing a baseline reference measurement network of about 100 plots to start with globally. And that, we reckon that's going to cost about 300,000 euros per plot for 5 years. So that's about 30 million euros in total. It sounds like a lot, but essentially you're going to get no change out of about 100 million euros for launching something into space and upwards. So, this is a key investment that really needs to be made. And so we're making this case at the moment that this investment needs to happen soon to build on the success of these satellite measurements. So this is building on existing networks, making those data accessible, making them shareable and fair, so that the people who contribute to those plot measurements have the benefit of using all the data that contributes to those measurements. And we're working on pilot projects in places like Brazil and Gabon at the moment. So just to finish up then, if you take a picture of this QR code, right at the beginning of when I spoke, Phil was scanning, like we did with Judy Dench's tree, and he scanned the inside of the auditorium here. So that link should take you to an online three-dimensional model where you can actually rotate the three-dimensional model of the inside of this auditorium to show you how we're using that technology. There it is. So there's the inside. That's you scanned in 3D by Phil. Well done, Phil, because we were having some technical problems here, but he managed to do it. Look at that. Never do live demos. Thank you.
Thank you. So I'm going to invite Frank Martin to make some closing remarks, if I may.
Thank you, John. Well, what did I take out of this 1 hour of presentation talks related to forestry, biomass, measuring? We need all kind of different technology, people on the ground, bringing all this together. Not one single technology, not one single measurement can give us the information which we need to understand the forest on the globe. And only by understanding it, pledges, like we heard during this week, to stop deforestation within this decade can make sense. We are all working together towards this goal. And I hope that this is not another goal set up in the future. It is something which should start now, because the planet needs the trees now.
If we can just like to thank all the organisations that have contributed to this. So we have, you've hopefully heard a whole lot of organisations mentioned, but just to say that We hope the video will be recorded and you'll be able to watch through again if you want to pick up particular organisations. We'll be available, I hope, afterwards for questions. So our experts, both at the panel and in the audience, we actually have some experts as well. So if you want to stay and talk either outside or round to the left is a Space for Climate stand. If you're online, please do contact us at nceo.ac.uk or Space for Climate, or indeed any of the collaborating organisations of the speakers. I think we've heard how a number of messages here, which I think are very important, and Frank Martins has articulated that very well. I hope you've heard that international collaboration is really important. We need to work together. I think there's a message from COP26 and all the COPs, it must be that. I hope you've also heard that there is a huge scientific community trying to support the activities, but also there are local organisations in every country trying to make a difference with these data, trying to bring you the best answer about how trees are influencing carbon, how that is helping the carbon story. We remind you again of the pledge for deforestation, but there are other activities going on. I hope you noticed the work around afforestation, that is planting of trees, and the importance of doing that in the right way for biodiversity, for cultural heritage almost, for the local livelihoods of people. And all of our speakers, I know in talking to them every day in preparation for this session, have really emphasised those remarks. So I'm really representing them in suggesting that. I just want to return you to this story of the carbon for a second. The Global Carbon Project, which releases a report every year, estimates that the land use emissions component of CO2 is about 4 gigatons of carbon per year. It's about 10% of the overall emissions into the atmosphere. So if you want to scale the deforestation pledge, now not all of that emissions is due to deforestation by any means, but if you want to scale that, we're talking about a 5 to 7% effect on carbon emissions, so roughly speaking. So it's quite significant. So just to put that in that carbon context. So we are trying to make progress, I think, in this COP 26, and I hope so afterwards. Of course, the secret, as you understood from these presentations, is to make sure we actually are measuring things and verifying and working together to have consistent results. So finally, can I just say that if you want to do more, I hope you are doing a lot to do with trees. You can do that yourself where you live. You can also join active forest campaigns. If you just go on the web, you'll find, for example, the Trillion Trees campaign, led by the World Wildlife Fund, Wildlife Conservation and BirdLife. You'll find Operation Ocelot, again, all trying to do things with trees. And you'll have seen discussions around carbon offsetting. So what I would say to you is always take care, always make sure things are being used in the right way. But most of all, thank you for giving up your time and attention to this. Thank you, everyone. Bye-bye.